All right, so it's about time for us to start. So written up here on the board, as always, we have our basic antiderivative / indefinite integrals. So the integral of x to the power a, as long as a is not -1, we can do the integrals of sine, cosine, secant squared, secant tangent. 1 over 1 plus x squared, that's our bonus for this class. And we can sometimes do definite integrals when we don't know how to do indefinite integrals. For example, in particular, I should say, not just for example, but there's one special case. If you look at the integral from 0 to 1 of the square root of 1 minus x squared, well, the square root of 1 minus x squared, that's actually hard to find an antiderivative for. It's not impossible. You can do it. But in this case, we're lucky because we recognize the shape. It's the part of a circle. And we know the area of a circle. That allows us to do the integral. So we can do that definite integral. And that's pretty much it. That's all we can do. So if we're going to do any kind of integration, sooner or later we have to get to this kind of point. So our goal is, whenever we're doing integration, we have to do an integral, which, using the fundamental theorem of calculus, one way to do integrals is to find antiderivatives. So finding antiderivatives is very, very important. So what's our goal? Well, our basic goal for doing integration is very simple. You simplify, simplify, simplify until you can integrate. And what do I mean by until you can integrate? Until you get one of these. Once you have something that looks like one of these on the board, then you can integrate it. Until you have one of those, you're basically stuck. And you have to work on rewriting it. Now, there's lots of ways to rewrite. You can use some algebraic identities. Sometimes you can multiply by a conjugate to get stuff out of the denominator. For instance, you can use trig identities. This is very useful whenever you have things involving sines and cosines, secants, and tangents. Basic rules of arithmetic. But one of the best ways to rewrite integrals is what we talked about last time. That's the substitution rule for integrals. So where does the substitution rule for integrals come from? Well, it comes from the chain rule for derivatives. And in fact, if you think about it, taking integration is essentially the opposite of taking derivatives. So it should be the case that rules for derivatives becomes rules for integration. And in fact, every rule that you have for derivatives, well, maybe not the quotient rule, but the chain rule becomes the substitution rule. And next quarter, you learn about the product rule. And that becomes what's known as integration by parts, but we don't get to do that. So you might remember the chain rule says, how do you take the derivative of a function inside of another function, f of g of x? Well, it's very simple. You take the derivative of the outside function. Inside stays the same times the derivative of the inside function. The substitution rule for integrals says, well, suppose I want to integrate something. And it looks of the following form. It has a function with another function inside of it. So f of g of x times by g prime of x dx. Well, what I can do is I can just basically change my names around just to help simplify the notation. And we'll say that, well, doing this integral here is the same thing as doing the integral of simply f of u du, where u is g of x. So this g of x is my u. And so essentially the idea is get rid of some clutter, simplify, spruce it up, spring cleaning. And hopefully this becomes simpler. And our goal is always to simplify, simplify, simplify. And then we get onto it. A very special case of this is, well, if we know how to do an integral f of t dt, we know what the antiderivative is. Then if I have f of at plus b dt, well, essentially it's the same antiderivative except at plus b plugged in times 1 over a. I mean, this is very easy to check if you use the fundamental theorem of calculus part 2, where you just take the derivative of both sides, and lo and behold, they match. Another way to see this is just use substitution. U is at plus b. So du is a dt, or if I use my fancy whiteboard technology, 1 over a du is dt, and then I just keep going from there. Now let me make some comments about substitution. Substitution is really important. I would say it's probably the most useful tool for working with integration. What do you look for? Well, you think about where the chain rule, the substitution rule comes from. It comes from the chain rule. Where does the chain rule come from? It comes from when you have a function inside of a function. So that's sort of your big hint that substitution might be useful, is when you see a function inside of a function. Now, that's not the only time you use substitution. But I would probably say this is one of the most common times you use substitution. I would probably say maybe 85, 90% of the time. Now, when you use substitution, what you're essentially doing is you're changing the problem from an integration involving x's to an integration involving u's. So what you need to make sure is you have to replace every single occurrence of the x by a u. And in particular, the dx has to become something involving du. So every single x has to become a u, one way or another. Now, another thing is that sometimes you have to manipulate the g prime of x and write it partially in terms of u. Now, in other words, we might have the case where u is g of x, which is fine. And then we have that du is g prime of x dx. But maybe we don't quite have g prime of x written down somewhere so conveniently as we would here. Oh, that's OK. We can massage. Sometimes. Sometimes we can't, but sometimes we can. Now, finally, let me mention, what if we're doing definite integrals? So this is indefinite integrals. Well, definite integrals, substitution works the exact same way. So again, if I'm integrating from a to b, f of g of x, g prime of x dx, I make my substitution. U is g of x, du is g prime of x dx, and I get a new integral from f of u du. But now, remember what I said up here. Every x has to become a u. Now, when we talk about integral from a to b, we're being a little bit lazy, because really what we talk about here is the integral from x equals a to x equals b. These a's and b's are x's. And remember, I have to replace every x by a u. So what I have to do is not only do I have to figure out what's going on with these x's in here, I also have to figure out what's going on with the bounds. Well, it's very easy to figure out what's going on with the bounds, because I know what u is in terms of x. U is g of x. So, for instance, if I know x equals a, I plug it in, and I see that my lower bound becomes u equals g of a. X equals b, I plug it in, u equals g of b. That becomes my upper bound. So these are now u values. And now I just keep going. Now, the best way to learn substitution, of course, is to do thousands and thousands of problems. We don't have enough time to do thousands of problems in class, so we'll just try to do a few today. Hopefully, you'll get some more in the homework. Don't worry, it gets easier. As I like to tell people, it's the first 1,000 that are always hard. And then after that, it gets a little bit easier. OK. So let's try some out. All right. Let's do a definite integral. This is, I showed some people this the other day. Suppose I ask you to integrate dx over x 1/2 plus x to the 3/2 from 1 up to 3. Now, I haven't written everything down here. There's actually, on this one, it comes with a hint. Because sometimes it takes a while to figure out what to do. So there's a hint on this one. Hint, u equals square root of x. Now, that makes it a little bit easier for us because we don't have to figure out the substitution. Usually, we don't have the hint. But when we have the hint, it's good to use it. OK. Well, let's see if we can make this work. So suppose I know that u is the square root of x. What would du be? Well, square root of x is another way of saying x to 1/2. And so I take the derivative of x to 1/2. A half comes down. X to minus a half times dx. Or, if you like, this is 1/2 times 1 over square root of x, because that's what x to minus 7/2 means. It means it goes down into the denominator, x to 1/2, so that's square root dx. OK, now looking at our integral here, this is the integral from 1 to 3. Notice what I can do with this integral. I can actually pull off an x to the 1/2. Because I have x to 1/2, I have x to 3/2. So let's just factor out x to 1/2. And if I do that, I get 1 plus x times x to 1/2. And this is good, because this dx over x to the 1/2, that's right here. So in particular, this part is easy now. That's simply 2 times du. All right, so this will become 2 times du on the end. How about this 1 over 1 plus x? What will that become? Well, it'll become 1 over 1 plus something. Those are just constants. So what does the x become? Well, what do we know about x? We know that u is square root of x. So in terms of u, what is x? X is u squared. Now, let's figure out the bounds. The bounds were originally from 1 to 3. What do the new bounds become? Well, I come back here. Again, u is square root of x. So when x is 1, what is the square root of 1? It's 1. So my bound here is 1. When x is 3, what is the square root of 3? Well, it's the square root of 3. So I plug the bounds 1, 3 into this function here to get the bounds. Now, of course, 2 is a constant. It comes out. And lo and behold, the integral that looked really mysterious now doesn't look very mysterious at all. In fact, it looks like one of those really cool integrals that Professor Butler really loves, arctangent. Aren't you so glad that we did arctangent? Otherwise, we couldn't have all these cool examples. Okay, so we have arctangent. This is good. So this is 2. I simplified to the point where I got to an integral that I could actually recognize. Arctangent u from 1 to root 3. So this is 2. Arctangent of root 3 minus 2 times arctangent of 1. Now, we have to test our knowledge of trigonometry. Do we know what the arctangent of root 3 is? Another way of saying that is, do I know what angle, when I take the tangent of that angle, gives me square root of 3? In this case, we do know, yeah, it's pi over 3. What angle, when I take the tangent of it, gives me 1? That's arctangent of 1. Pi over 4. And if you simplify, we get our final answer, pi 6. Okay. So there's an example. Let's do a few more. Suppose I ask, let's do some indefinite integrals. The integral of x, let's do an integral of x squared, square root of x cubed plus 1 dx. All right. There's no hint on this one. So we have to figure out what the substitution is. So how do we figure out what to substitute? Figure out how to substitute. We come back to this, pretty much the first and most important comment about substitution. Substitution is made for functions inside of functions. So if I'm looking for what to substitute, I'm looking for a function inside of a function. In this case, there's something that screams out, pick me, pick me. Because I see there's an x cubed plus 1 inside a square root. So x cubed plus 1 is a function inside of another function. So that tells us. It's like trying to telegraph. I'm it over here. Okay. Now hopefully this works out. Let's see how far we can get. What's du going to be? Yeah, 3x squared dx. And we see, we lucked out. So I have an x squared dx. And what I can do is I can just take that 3 and put it over here. So 1/3 du is x squared dx. And now we're in great shape. So the x squared dx becomes 1/3 du. And then the square root of x cubed plus 1 becomes square root of u. Or if you like, this is the integral of 1/3 comes out, u to the 1/2. And now, very easy. So to do this integral, add 1 to the exponent, so u to the 3/2, and then times by the reciprocal of the exponent, 2/3, add a c. So this is 2/9. And then I have to get back in terms of x. Because I started in terms of x. So my answer better be in terms of x. Well, I know this is u to the 3/2, so I come back and say, well, what is u? U is x cubed plus 1, so I rewrite x cubed plus 1 here to the 3/2. Okay. That was good. Let's try a different one. Suppose instead of this integral, I ask you for the integral of x cubed, square root x squared plus 1 dx. Now what do we do? Okay, long dramatic pause. So now we're like in midterm mode. Long dramatic pause, and we stare at this for a long time. But it's no different than before. Again, it's always the same thing. Look for a function inside a function. This works, I would say, approximately 90% of the time. And then the 10% of the time it doesn't work. Most of the time we'll have a hint. Or I'll be prodding. Okay, so here, there's something, again, it just is saying, please, it's me. Pick me. Where do I have a function in a function? Oh, right there, exactly, yes. Here, the x squared plus 1 is inside the square root function, so that's what we should choose. Now, sometimes it takes a while. We might have several possibilities, and it's good to play around with it. Most of the time right now, it should be hopefully fairly obvious. Okay, so du is 2x dx, and just for convenience, I'm just going to move the 2 back over here. So half du is x dx. Now, over here, we were pretty happy because I had an x squared dx, and that was just automatically became my du. Now, the problem is I don't have a x dx. I have an x cubed dx. So we have to figure out how to deal with that. So one way we can deal with that is we can say, well, look, what is x cubed? Really, x cubed looks like x squared times x. Not very profound, but I'm just breaking it off. Now, why do I break it off? Well, because I need that x to join up with my dx, and that will become my du. So this x dx becomes my du. And then I say, well, I still have to figure out what to do with this x squared. So what can we do with the x squared? Yeah, I can solve for x squared. In particular, whatever's left over, I have to figure out how to write in terms of u. Now, in this case, it's fairly easy to solve for x squared. X squared is u minus 1. So, making all our substitutions, the x squared becomes u minus 1. The square root of x squared plus 1 becomes square root of u. And the x dx becomes 1/2 du. Okay, so now we're getting closer. It certainly looks nicer than what we start off with, but it's not quite as nice as I would like. What are some things we can do now? Well, one thing we can do now is certainly we can bring the constant out in front. And the other thing is that I can multiply out, expand, if you will. Okay, so square root of u times u is u to the 3/2. We're still integrating. And then square root of u times 1, well, it's simply square root of u, or u to the 1/2. And now I'm happy, because now I have something. It's in one of these forms, in particular the one up in the corner. So now I can just simply work it out. So the integral of u to the 3/2, well, I add 1, 5/2, multiplied by 2/5. And then u to 1/2, I add 1, so to the exponent, that becomes 3/2 multiplied by 2/3. And I add c. So this becomes 1/5 times u to the 5/2. But now I come back and replace what u is. X squared plus 1 to the 5/2 minus, and then 1/2 times 2/3 is 1/3, and x squared plus 1 to the 3/2, and then plus c. Okay, so far, so good. Let's do one more. Suppose I ask you to integrate secant squared x tangent x dx. Now, in this case, we're really not in the case where we have a function inside of a function. But I think we can figure it out. So I'm looking for a function to substitute. And I also want to have the derivative somewhere in there to help sort of get all absorbed into the du term. So what's something we can try? Okay, we can try secant. Let's try that. If u equals secant x, what would du be? Secant x tangent x. Now notice what I have. I can break off with secant x, so I can really think of this as secant x times secant x tangent x. Aha. So then we get that this is the integral of of u times du. The integral of that is a half u squared plus c. So that's a half secant squared x plus c. Okay, good. Could we have chosen something else to do the integral? All right, let me rephrase the question. Could we have chosen something else to do the integral? And what else could we have chosen? Okay, let's go back to the first question. Could we have chosen something else? Yeah, we could have chosen something else. We could have tried tangent. Now, sometimes more than one substitution works. It's kind of rare. Usually, it's in examples like this which we cook up. But it happens. What's the derivative of tangent? Secant squared. And notice, what do I have? I have a tangent that's acting. Oh, oops, I forgot my dx up here. dx. In this case, the tangent's acting as my u, and my secant squared x dx is acting as my du. So again, I get the integral of u du. So this is a half u squared plus c. So this is a half tangent squared x plus c. Now, you might stop for a second and say, wait a second, hold on. You did this antiderivative, but you got two different answers. You did it one way, you got a half secant squared. And you did it another way, and you got a half tangent squared. Wait, which one of these is right? Because they don't match. Or do they? Right. There's this identity that says if you look at secant squared x, it's tangent squared x plus 1. So even though these look the same, they differ by what? They differ by a constant. That's why we have these constants here. So it looks like they're two different solutions, but they're not two different solutions. They're really the same solution, just slightly shifted by a constant. And we're using the fact that secant squared plus tangent squared to recognize that. Okay. All right, well, that's enough for doing substitutional. Don't worry, you'll get lots more practice on homework and on the final. Woohoo! I guess I gave it away. There's a substitution problem on the final. Actually, I'm thinking of changing it because the substitution on the final now is too easy. I know you guys want a challenge. All right. Okay, so today, our topic, topic for the day is area between curves. Now, this doesn't write that well either. Now, it's not very surprising how to find the area between curves. Why? Well, because we thought about this integral, a to b f of x dx, and this is what we call the signed area. Between y equals f of x and the x-axis. And that's how we interpret it. That's how we came up with what does integration represent. Well, one way to think about it is in terms of signed area. Now, here, when we talk about signed area, if I'm integrating from a up to b, well, if I'm above the x-axis, then this is, we think of as positive area. And if I'm below the x-axis, I think of it as negative area. But it should be pretty easy to convince ourselves that integration has something to do with area. So if I'm looking for area, integration seems like a very obvious choice. And here we have. So suppose we have f of x is strictly greater than or equal to g of x on the interval a less than or equal to x less than or equal to b. So I have two functions. F is on top. So here's function y equals f of x. Here's the function y equals g of x. And I'm looking between x equals a and x equals b. Now, I only care about what happens from a to b. I don't care if over here they cross. As long as just between a and b, f is on top and g is on the bottom. That's all I really care about. I don't care what happens outside from a to b. And I'm interested in trying to figure out what's the area of this graph between these two curves. So the area between f of x and g of x, between a and x equals a and x equals b. It takes us longer to say what we're looking for than actually to write down the equation, is simply the integral from a to b f of x minus g of x dx. Now, there's a couple of ways to see this. One intuitive way is, well, you think about the picture. What's the integral from a to b of f of x finding? Well, it's really finding the area from f of x all the way down to the x-axis. So it's finding that area there. That's the integral from a to b of f of x. Well, okay, so let me write. Okay. What's the integral from a to b of g of x find? Well, the integral from a to b of g of x finds this area. And then, lo and behold, it's not too hard to see. If I'm looking for the red area, I simply take the big blue area minus the little blue area, which is this. And that's one way to see it. But there's a better way to see it. And I think this is how I like to think of it, because I think about what integration represents. Integration says you break things up into little tiny pieces, figure out what's happening with each little piece, and you add it back up. Now, in this case, the way I like to think about it is I like to think about it as splitting up into little tiny rectangles. So imagine going from a to b, and I'm just slicing up into little tiny rectangles. In this case, I'm taking these slices in a vertical direction, vertical slices. And I say, okay, what's the area of one of these little slices here? Well, if it's a little tiny rectangle, I have a width. In this case, it's dx. I also have a height, which is this length here. Well, what's the height? It's the difference between the two curves. So the height is f of x minus g of x. So if I come to this integral, which I'm starting to write diagonally, I notice, this is the area of a tiny vertical slice. Here. And then once I know the area of one of my little slices, all I need to do is add them up. And that's what integration does. Integration is adding up lots of little tiny pieces together. Remember what the integration sign comes from. It's an S for sum. So you're adding lots of stuff up. So that's how I like to think of it intuitively. That helps me remember the picture. So now with this picture, it's actually fairly straightforward to go through and do tons of problems. Okay. So now we just start writing down problems galore. Okay. And this will just be practice doing lots of definite integrals. Because notice that an area is a value. So we're going to integrate from a starting point to an ending point. So this is really going to be our practice of doing definite integrals. Okay, so suppose I ask the following. Find the area between f of x equals 1 plus x squared and g of x equals 2 minus x. Oh, wait, sorry. Let me do negative x squared for -1 less than or equal to x less than or equal to 3. Let's suppose I ask for this question. We'll do a very simple one first. So 1 plus x squared looks like this. And negative x squared looks like this. So it's helpful to figure out which function's on top, because oftentimes we'll say there's two functions, but we won't say which one's on top. And if we're really mean, we'll give you two functions which cross somewhere in the middle. And if they cross somewhere in the middle, you have to figure out, okay, where do they cross? How do I change my sign? So we want to go from -1 up to 3. Okay? And so we're looking for this area here. So now we can see which one's on top. We see what our bounds are. So it's going to go from -1 up to 3. The top function, 1 plus x squared minus the bottom function, dx. So I guess I should also point this out. Another way to remember it is instead of thinking of it as f of x minus g of x, just think of it as the top minus the bottom. Whichever function's on the top, subtract whichever function's on the bottom. That just gives you the height. And what does this become? -1 to 3. 1 plus x squared minus minus becomes 1 plus 2x squared dx. And this is a simple integral for us to do. So this is x plus 2/3 x squared, evaluated from -1 to 3, which is 3 plus 6 makes 9, minus -1 plus 2/3, so that's minus 1/3. So this is 28/3. All right. Now, I went through and did this problem, and at no time did I get nervous about the fact that this function g of x is actually negative. I didn't even notice it because I don't need to worry about it. I don't need to worry about the fact whether the function f is positive or negative, or g of x is positive or negative. Or they somehow go below or above the x-axis. It doesn't matter. As long as I think of this fact that f of x minus g of x always is representing the height between the curves. It doesn't matter whether I have one function going below the x-axis or not. So don't worry about, oh no, the function g of x is negative, what do? You don't change anything. It's always the exact same formula. All right. Now this is very easy because I said, okay, here's two functions. It's clear which one's on top, which one's on the bottom. And then I say, here are my bounds. We're not always going to be that nice. So, in particular, I might not give you the bounds, and I probably won't tell you which one's on top and which one's on the bottom. So when you don't have bounds, then you have to figure out what's going on. So for instance, suppose I ask for the area of the region bounded by y equals x squared and y equals 2 over x squared plus 1. But I'm not telling you from this point to this point. I'm just saying, here's two curves. I want you to find the area. Now, you have to think about, well, what do I mean? Well, I'm talking about if you graph the picture here, there's going to be some piece, which is some finite piece which you can measure. So these curves turn out to be fairly simple, so we can actually graph them. Y equals x squared is a parabola, which looks something like this. And 2 over x squared plus 1, we've seen that on a few homework assignments. It looks a little bit like the bell curve. It's not the bell curve, but it looks like it. It might be mistaken for, in a dark alley at night. Okay, so here are our two curves, and you'll notice that essentially when I draw these curves, I'm breaking the plane up into pieces. If I imagine I just take my scissors and cut out. Now, most of these pieces are big, are infinite, I should say. But there's one piece which is not infinite. It's small, and it's this piece here. So when I'm talking about finding the area of the region that's bounded by it, I mean finding this area here. Okay, so now we understand this is the area we're going to find. And the picture helps us to see that, well, I know which one's on the top, It's the 2 over x squared plus 1. And I know which one's on the bottom. It's the x squared. But I don't know something. I have to figure out my bounds. So how do we figure out the bounds? Well, if I think about it, what's special about this point? It's where the curves are intersecting. Where the curves intersect says that these two functions have to match. So x squared has to equal 2 over x squared plus 1. Or x squared times x squared plus 1 equals 2. If you like, x squared squared plus x squared minus 2 equals 0. That's another way to write this equation. Now what can I do to solve for x? Well, here, in some sense, this is a quartic because it has x to the fourth. But I've written it in kind of a strange way where I've written x squared squared and x squared minus 2. This is really a quadratic, but instead of a quadratic of x, it's a quadratic of x squared. So I can use the quadratic formula to say, well, x squared equals negative b plus or minus the square root of, let's see, did I do this right? Okay, negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so we simplify. 1 minus 4 times negative 1 times negative 2 is negative 8. So this is 1 plus 8, which is 9. Square root of 9 is 3. So I'll just replace that by 3. So this is negative 1 plus 3 over 2, which is 2 over 2, or simply 1. 1. Or negative 1 minus 3 over 2 is negative 2. Now, which one of these can we throw out right away? I have x squared. Can it ever be negative 2? No. X squared is positive in our class. So that tells me that where the points of intersection occur are when x squared equals 1. Well, when does that happen? Yeah, it happens negative 1 and 1. So now we have the bounds. So oftentimes on these area problems, a big part of the problem is figuring out, all right, where do I go between? From where to where? And once you have that figured out, then the rest of it is just very straightforward doing the integral problem. So I know I'm going to go from negative 1 to 1. The top function, 2 over x squared plus 1, minus the bottom function, x squared dx. Now, we can also save ourselves a little bit of work if we want to. Notice that here, these graphs have symmetry. They're both even functions. So sometimes, if you're in that case, you can actually, instead of integrating from negative 1 to 1, you can integrate from 0 to 1 and just double whatever you get. Oftentimes, it turns out it's much easier to when you have 0 as one of your bounds, just because many functions, when you take the antiderivative and evaluate at 0, you get 0. And this is simply saying nothing more than, look, this area on the left is the exact same as this area on the right. So if I just find one of the two and double, then I'll get what I want. So let's actually save ourselves a step and do that. If you don't like that, you don't have to do it. You can still do this. You'll get the same answer both ways. Okay. So we go through. All right. So this becomes 2 times 2 is 4. And the antiderivative of 1 over x squared plus 1 is arctangent of x. Then antiderivative of negative 2x squared is negative 2/3 x cubed. And we evaluate from 0 to 1. So this is 4 arctangent of 1 minus 2/3 times 1 cubed. And now when I plug in x equals 0, arctangent of 0 is 0. 0 cubed is 0, so I get 0, which is one of the nice things about having 0 as one of your bounds. And we already did arctangent of 1 is pi fourths times 4 is pi minus 2/3. So pi minus 2/3. Okay. All right. So there's that one. Now, we don't have to integrate just with respect to x. We can also integrate with respect to y. So in particular, I might have some function here where I have x is g of y, x is a function of y, and I might have another function over here, x is f of y. And again, I'm looking for the area from y equals a to y. Sorry, let me get this. Between y equals a and y equals b, I might want to find this area here. So sometimes it's easier to have your function represented as a function of y than as a function of x. How do we do it? Well, if we think about this formula here, okay, unfortunately we're losing half of it. Well, if we think about how we got it, the way we did it is we thought, well, let's just take a little tiny strip. Now, instead of doing a vertical slice, let's do horizontal slices. The reason I'm saying horizontal slices is I'm integrating with respect to y, not with respect to x. And I say, well, okay, what's the area of a little slice? Well, I have this height is simply dy. And then I say, well, what's this width here? Well, it's the difference between the two x values. And I say, well, I want to take the larger x value, subtract the smaller x value. Or if you like, this is the right minus the left. The higher value, subtract the lower value. So that the area of this little tiny slice is simply f of y minus g of y dy. So that's the area of one little slice, and of course I want to add up all the little slices up, so I go from a up to b. So in essence, it's the exact same formula, so there's no surprise. So let's try a problem. Suppose I ask, what's the area bounded by y equals x squared and x equals y cubed? Suppose I ask this question. And let's find it in two different ways. Let's find it first if we integrate with respect to x, and then let's find it if we integrate with respect to y, just to get practice. And hopefully we should get the same answer for both. So first off, what do the pictures look like? Y equals x squared, well, we know that looks like a parabola. What about x equals y cubed? Well, this is the same as saying y equals x to 1/3. Or, well, there's a couple ways to do that. Okay, so here, this is my x equals y cubed, or y equals x to 1/3. Two ways to think about this curve. Now, this curve here, this is the y equals x squared, but you can also think of it as x is the square root of y. And notice we have this region. So we're really trying to find that region. Now, clearly, by the way I've drawn this picture, they intersect at 0, 0. And it's easy to check. 0 equals 0 squared, 0 equals 0 cubed. Where else do they intersect? Yeah, they intersect over here in this other corner at 1, 1. 1 equals 1 squared, 1 equals 1 cubed. Okay, so let's find the area. Okay, area with respect to x first. So I'm going to integrate. My bounds will be from the small x value, 0, to the large x value, which will be 1. So if we're integrating with respect to x, I'm taking my vertical slices, and I say, what's the top function? Subtract what's the bottom function. In this case, the top function is the x equals y cubed, or y equals x to 1/3. Subtract this y equals x squared. So x to 1/3 minus x squared dx. Now, we can do this integral. I add 1 to the exponent and get x to 4/3. Then I times it by the reciprocal, 3/4, minus x cubed times the reciprocal, 1/3. And I evaluate from 0 to 1, which is 3/4 minus 1/3. And I plug in 0, I get 0. Well, what's the common denominator? 12. 9/12 minus 4/12 is 5/12. Okay, so when I integrate with respect to x, here is my integral. I integrate with the top minus the bottom. Let's find the area with respect to y. Okay. Well, again, I come here and say, okay, what's my low y value where they intersect is at 0? And then the high value where they intersect is at 1. So my bounds are the same. Of course, these are not bounds in terms of x. These are y bounds. So I'm integrating with respect to y, dy. Now I'm going to take the right minus the left. So in this case, the right function is this function here, which is the x is root y. So, or if you like, y to the 1/2. Subtract this function here. That's the left function. In that case, it's the x equals y cubed. Okay, so this is y to the 3/2 times 2/3 minus y to the 4th times a 4th. Evaluate from 0 to 1. So that's 2/3 minus a 4th. Now, not quite that, but let's see, maybe when we simplify. So that's 8/12 minus 3/12. Aha! We got the same answer, which is good, because we were computing the same area. So if we compute the same area using two different integrals, of course, then we should get the same answer. Now, let me mention one other problem. We'll do a few more next time as well. Now, in this case, the curves are y is 2 times the absolute value of x, and y is 9 plus 5x minus 2x squared. Okay, so let's think about how we would go about solving this problem. Well, intuitively, what we do is we try to get a grasp of the picture of what's going on. Now, maybe we can't draw things perfectly, but we can get a really rough sketch of what's going on, because I know what absolute value of x is. So 2 absolute value of x is kind of a V shape. I know it's doing something like that. I don't, up to, some bad drawing, but it looks like that. What is this kind of a function? It's a parabola. Which way does it open, up or down? Down, because it has a negative. And it also, if we look at the y-intercept, we know the y-intercept is at 9. Now, I don't know exactly what it looks like. Let's pretend it looks something like, let's see, I'm going to get myself in trouble if I just try to do this at random. Let's pretend it looks something like this, more or less. Now, again, I might be wrong. It might look the other way. More or less, it looks something like this. So how would we go about solving this problem? Well, what's our first step? Yeah, we've got to find the bounds. So we're going to have to set 9 plus 5x minus 2x squared equals to 2 absolute value of x and solve. Now, how would we possibly solve this? Well, we kind of have an idea. We know that essentially that there is a solution over here for x bigger than 0, because we know it has to go through here and it has to go down. So it has to go down. So it has to intersect somewhere. So really, it's going to break into two problems. 9 plus 5x minus 2x squared equals 2x, and this will help us find the x greater than 0 intersection. And 9 plus 5x minus 2x squared equals negative 2x, and this will help us find the x less than 0 intersection. So we actually have to do two problems to figure out the intersection points. And we'll find these. Okay, now we found the intersection points. Now we do the integral. And when we do the integral, well, it's going to be the top minus the bottom. But how do I integrate something which has this absolute value of x in it? Yeah, we're going to break it up. So that's the other piece of this. Is if you have several curves defined, in this case, you can think of it as, well, I have this curve over here, and I have this curve over here. Well, just break it up into two pieces. So that's the other thing we'll do. We're going to figure out the bounds. And then we'll say, okay, what's this piece over here? Because then I can drop absolute values. And I'm going to say, what's this piece over here? Because I can drop absolute values over here if I'm just working at that. I add the two together, and I'll get my final answer. All right. See you on Monday. Don't forget to turn in your penultimate assignment before you leave. Woohoo! Penultimate!